In this video, we look at one of the simplest types of regularization methods, making sure that our network parameters don't get too large. Let's dive right in. Preference for small weights. A very popular type of regularization method in machine learning are so-called shrinkage methods. They're called shrinkage because they're trying to shrink the parameters towards zero. And the way they do this is they write a loss, so they put the regularizer into the loss function, and the combined loss function is the data dependent loss, so how well do you actually fit your data, and to that they add a regularizer, and they multiply this with a hyperparameter lambda, that is the strength of this regularizer. This regularizer then penalizes large weights, and it does so by taking each individual weight and taking it to the power of q, and then different q's give you different regularizer. So q of 2 gives you L2 regularization, that gives you quadratic penalties, and a q of 1 gives you this L1 regularizer, also called lasso in the literature. So we can visualize how these regularizers act by looking at their contour lines. So these contour lines tell us what types of weight values are equivalent in terms of this penalty function. So what we're plotting here is the weight for θ1 and for θ2, let's say. And this L1 regularizer here says I don't have any preference over having this value that has a θ1 of, let's say for the sake of argument, 2, and a θ2 of 0, or of a θ2 of 2 and a θ1 of 0, or of likewise the case where θ1 and θ2 are both 1. In contrast, if we have L2 regularization, then there's no preference between these 2 points and this point here, which actually has square root of 2 for both of these parameters. And so this resulting L2 regularizer here is often more analytically tractable, for example, in ridge regression. But with a lower q, such as q equal 1, we actually have the property that we will pick solutions that have some weights actually set to exactly 0. And the reason that is illustrated on this slide here. So here in red, we have a contour of the penalizer, and in blue, we have different contour lines of the data-dependent loss. And so let's say we are ready to accept a penalizer that is this large here. It could also be smaller, such as here or so, but we're not ready to accept a penalizer that is outside of this ball here somewhere. Then what we will actually pick under this data-dependent loss here in blue is precisely this point where one of these outer contours of the blue data-dependent loss intersects with this penalizer. And when we then look on the right side here for the L1 loss, there we see that actually if we're ready to pay this penalty only up to here, then, well, this here would actually be a higher penalty. That would be the solution that we picked for L2. And we're not picking it, but we pick this point here, which for which the θ1 is 0. So this weight, θ1, is just completely turned off, and we could actually just drop the entire connection. Also, of course, in traditional machine learning, where we have human engineered features, it's nice if we can drop some features, because then we don't actually need to measure them in the data. So that's why L1 is actually very popular in the literature. All right, and L2 regularization is actually what's very often used in deep learning. And it is typically implemented by directly changing the gradient. So we'll have the gradient prime is now the gradient of the data plus the gradient of this L2 loss here. And well, the gradient of this L2 loss is conveniently just, well, lambda times this L2 loss is just lambda times the total size of the parameters. And you simply add that to your gradient. And that's a very convenient way to implement L2 regularization directly in neural networks by simply adding it to the gradient and then changing the SGD update from the standard theta goes to theta minus the learning rate alpha times G. Now we have this G prime here. And well, then we can simply plug in this G prime here and rewrite this as follows also. This rewriting is convenient when we want to relate this L2 regularization to a classic technique that was already introduced in 1988 that is called decoupled weight decay. So this doesn't actually talk about an objective function and a regularizer that's added to the objective function or the data-dependent loss, but it rather says, just at every step of SGD, I want to pull my weights towards 0 a little bit by taking the current weights and multiplying them by a certain 1 minus W. And W is something between 0 and 1 and typically relatively small. So we just change, we multiplicatively change the weights a little bit to pull them a little bit towards 0. And in this equation, you then have just the learning rate times the standard gradient of the data-dependent loss. And when we look at these two terms here, then we see that for SGD, this is actually identical to L2 regularization, except here we have a learning rate times the L2 regularization strength, and here we just have this weight decay. So this is identical if we set the regularizer to weight decay divided by the learning rate. And that is precisely why L2 regularization in deep learning is actually often called weight decay. Now, one thing to note actually is that the hyperparameters lambda and the learning rate, so the strengths of the L2 regularizer and the learning rate, are actually coupled in L2 regularization. If you want to obtain the same value of this weight decay, and you also then, if you change the learning rate, and you often do need to change the learning rate in deep learning, as we've seen, then you actually also need to change the regularizer in order to get the same value of the weight decay. And in practice, you would actually typically like to have the same value of the weight decay as is shown in these figures here. So here we have a plot that's on the y-axis has the initial learning rate, and here we have L2 regularization, and we have in red, we have very poor values of the objective function of validation loss in this case, and in blue we have very good ones. And we see that there is this region here that is actually very good, and that lies very close to the diagonal. So if you actually have a point where currently your learning rate is here and your L2 regularizer is there, then, well, that's a very suboptimal hyperparameter setting. But if you just change the learning rate to a better value, something that's in this region here, well, you change the learning rate to be higher, but that actually makes things worse. So it makes hyperparameter optimization harder to have this coupling. So you need to actually, when you increase the learning rate, then you also need to reduce your regularization factor in order to compensate for that to get the same weight decay, because, well, the weight decay is just the learning rate times your L2 regularization. On the other hand, on the right here, we have a plot where here we have the initial learning rate and here we have the weight decay. And yeah, there you have the fact that, well, this area of good performance is just very axis aligned. So you can do hyperparameter optimization by changing one parameter at a time here. And it's also much easier for humans to understand than when you have this coupling, these dependency effects, these interaction effects between two different hyperparameters. So we saw decoupled weight decay for SGD, and there we saw that that is equivalent to L2 regularization modulo this reparameterization of W and lambda. But actually, if you have adaptive gradient algorithms, their decoupled weight decay is not the same as L2 regularization. And there's also no constant that you can just multiply with your weight decay in order to get L2 regularization. And the reason for that is as follows. So for decoupled weight decay, what you do is you simply take your gradients of the loss function and you run your adaptive gradient computation on that. And then completely decoupled from that, you do your weight decay. So at the beginning of each step, you just multiply your weights by 1 minus W, and then you also subtract the adapted gradient. So in L2 regularization, however, the adaptive gradient computation is happening on the combined gradient G prime of this combined loss function that is a data-dependent loss plus a regularization loss. And there we actually need to remind ourselves how do adaptive gradient algorithms work. Well, adaptive gradient algorithms typically take the gradients and divide them by some approximation of the historical magnitude of the gradient. And so if we have a particular weight that is very important for the loss function, so if you change this weight, the loss function changes a lot, then this particular weight will have historical large gradients. So you actually will divide its gradients by something large. And well, you'll also have the regularizer for that particular weight divided by something large. So you actually take the weights that have historically been important and you regularize them less. So you allow those weights to wiggle a lot, and that can give you a lot of variance, and that can actually be pretty bad. And that actually leads to the fact that Adam can actually generalize a lot better when you use decoupled weight decay. And that gives rise to the popular variant AdamW, Adam with decoupled weight decay. And here's a visualization again, where, well, also you have these somewhat more diagonal looking surfaces. But more importantly, the color here, you don't see any real blue color in here, whereas in this decoupled weight decay, there is much more blue color. In the blue color are these much better performances. And just in the whole range of the regularization parameter and the initial learning rate, there is actually just no combination of those two that leads to as good generalization as when you use decoupled weight decay. So here you don't have an equivalence anymore, but decoupled weight decay can actually give you better generalization. All right, this brings us to the end of this video. And as always, I'd like to leave you with some questions. So I encourage you to pause the video here and think about them before moving on. And I'll see you in the next video. Thanks.